Okay, so here's our lesson on simplifying radicals. And this should hopefully look somewhat familiar to grade 10, because we're going to kind of start in a place that I know Juan would have taught you last year, and then we're going to extend it a little bit further. For some of you who already looked at the assignment, it really doesn't matter about -1 or -2 just yet. But last year, you guys should have learned how to deal with taking a number and turning it from an entire to a mixed radical. Today, what we're going to add to it is throwing in some variables, like x's and y's and p's and q's. So let's start with some review. Do you guys recognize like the difference between an entire and a mixed radical from last year? Essentially, the entire radical means that the entire number is out of the square root sign. Whereas here, a mixed radical, there's a number in front of the square root sign. But these things are the same as each other. I'll prove it to you with the calculator. If I find the square root of 72, it's equal to that number. But if I do 6 and then do the square root of 2 right afterwards, it's also equal to that number. This is it's known as like simplifying a radical. So it's not always possible to convert something into this mixed form, but hopefully this looks familiar. Let's talk about radicals a bit more, some of the technical stuff. You cannot have a negative sign under the square root. You said this before? It's just one of those cardinal rules of math. You can't divide by 0, it's just not allowed. You can't try to square root a negative number. It's just not possible. You don't know why. Why is it not possible to square root other than my teacher told me I couldn't, so I believe him? What does a square root imply? Go for it.
Like something multiplied by something. Like saying that multiplied by each other.
Yeah, essentially that's what it means. Square root is the opposite of like squaring a number. What does squaring a number mean? Well, like Rebecca said, you're taking the same number and you're multiplying it by itself. Is it possible to take a number, multiply by itself, and have it be negative? The answer is no. It's positive times positive is positive. Negative times negative is actually also positive. So therefore, it's not possible to like undo a squared sign with a square root, somehow have it be negative. It doesn't work. Okay, other terms we should know. These are considered to be like radicals. Kind of like with the word like terms. If I gave you 3x and 4x, you can actually add them together to get 7x because, well, they have the same x. Well, the same thing happens to radicals. This is a 1 root 5. This is a 4 root 5. Sometimes I'll say, like, you have 1 of something, you add 4 of something. It means that if you added them, you'd have 5 of something. Our something is a root 5. So you can actually put them together if they have like radicals. But they have to be the same. If I gave you a root 5 and 2 root 3, they cannot go together. That's like the apples and oranges analogy. You can't add them together. The last note I have on here, there are some numbers that are actually considered to be perfect squares. Like say 16. 16 just straight up turns into 4. 17, that doesn't work for, right? But there are certain numbers that just straight up square root to a whole number. Like 2, no, 4 turns into 2, right? 9, 3. You guys know some of these numbers? Okay, so that's actually what we're going to work on today. We're going to build on yesterday's topic of factoring, and we're going to practice reducing some values. A few more things before I get to it. I'm kind of building my way up. What does a square root really mean? Well, it's almost like you're trying to undo a squared sign. Maybe you've never seen it approached this way before, but is 25 not written as 5 squared? Well, this squared sign and this square root sign, they're opposites. You know how adding and subtracting are opposites, multiplying and dividing, squaring and square rooting are opposites. So if you can find a number like 25 or 9 or 16 that can be squared, then it can just give you a whole number. I don't know whether you guys did a lot of cubes last year. Did you do cubes?
Sometimes.
Okay. Maybe a little bit. We're going to add that a little more this year then. The same principle applies to cubes then. If you want to try to cube root a number, it better be able to be written to the power of 3. 125 is 5 to the 3. This cubed root and the power of 3, essentially they cancel each other. That's the logic of it. So here's what you should have done last year. I don't know exactly how Quan would have demonstrated it, but maybe it looks like this. You do the 50 breaks up into 2 and 25, and 25 breaks up into 5 and 5, like what Mr. Bond did yesterday. The idea here would be that if you have 2 5s, that's really 5 squared. But you're being asked to square root. So doesn't the squared and the square root kind of cancel? And essentially what happens is these 2 5s get pulled outside the square root side. Is this something that looks familiar? What I like to recommend, though, is to not go all the way down to prime factors. Not that prime factoring is wrong, but I'm going to recommend we stop right here. The reason why is that once you recognize these values, isn't 25 a number that you can actually square root? 25 square root's 2, 5. So then bring the 5 outside. That's what we're going to practice doing at the start. I'm going to come back to this slide. Let's do this. Skip that one. So let's start with the root of 200. You could start with the factor tree and just start looking for all the numbers that go into 200. Like, for example, it could be 20 and 10. That's not wrong. But I've said this to a lot of you already this year. We're at the point in math where you can do mathematical operations. You're not incorrect, but it's not helpful. And I don't think this is actually helpful. Because are either 20 or 10 square rootable numbers? Let's try to find a square rootable number that goes into 200. 2 and 100. That's more useful. Not that 10 and 20 was wrong, but which of these numbers is the useful number to us? 100, right? Because 100 can square root 2. So our answer is 10 from the square rooting of the 100. But can the 2 actually square root? So it stays behind. We would say this then, like verbally, the way you read this out loud, you would call this 10 root 2. That's how you say it out loud. You'd say 10 root 2. And that's considered simplified, which is what you should have done last year. Okay, now that I've reviewed all of grade 10 in 5 minutes, now we gotta start adding some new stuff to it. Did you guys do stuff like this last year?
Nope.
Yeah, probably, maybe you forgot. So I want to go back a slide now. I want to talk about what was on this slide. Maybe you did, maybe you just forgot. There's a rule about exponents that you should have covered at some point. And basically it says this: if you have a 1/2 exponent, it's a square root. If you have a 1/3 exponent, it's a cubed root. If you have a 1/4 exponent, it's a 4th root. Once you figure out the pattern, it's actually not that hard. The bottom number on the fraction is the kind of root you happen to have. If it's a square root, though, we don't bother putting it 2 here. So hopefully you've learned this rule at some point before. Say it again. Okay. So let's try this one right here. Is there a fraction involved? Yeah, it totally is. The bottom of the fraction is a 3. What this means then is I'm actually asking you to cube root. Well, what's left? We use the over 3 part. So I'm actually asking you to cube root x to the 8. Well, we still have a little more work to do though. You know how we had the 200 sitting right here and it can get broken up into pieces? I kind of need to break the x to the 8 up into pieces as well. What does x to the power of 8 really mean mathematically? 8 x's, but all times by each other. It doesn't mean 8x. That's not it. It means x times x times x times x. And I'm actually going to write out 8 of them for the visual here. Is that 8? That's 8. That's what x to the 8 really means. You need 8 of them. We're cube rooting. We need things in groups of 3. So in a way, would it not make sense that this right here is an x to the 3? This right here is also an x to the 3. Not quite enough. So what ends up happening then is when I cube root this x to the 3, I just get an x. And when I cube root this x to the 3, I get another x. So what I really have is one x from cube rooting this bit, another x from cube rooting this bit, and then this is an x squared. And I'm going to try to cube root it. I don't have enough though, do I, right? So that's the stuff that has to like stay under the square root. Just like how this 2 from the previous question had to kind of stay behind. The x squared is going to have to stay behind. So of our 8 x's, 3 came out as 1, another 3 came out as a second one, and the 2 got stuck. But we can actually put these 2 x's together. Like there's a better way of writing that. You want to take a stab at it? X squared, yeah. So the final best answer of writing this would be saying you have an x squared on the outside, and then you're still cube rooting an x squared on the inside.
Come to the office, Rod and Mike. Please come to the office.
Oh boy. So this is probably the part that's now kind of it's similar to what you've done before. But it's the new little twist, is we're going to deal with a lot more cubed roots than maybe you've done in the past. We're also going to throw some fraction exponents in there. And now we're working with letters a little more often. But honestly, once you get the hang of it, it's not that bad. Try the next one. You just deal with numbers and letters independently, that's all. 63. We need to break 63 up into some sort of factor, and I want one of them to be something that can square root. Yeah, 7 and 9 is a good call. I mean, you could have done other possibilities, but the reason why Joe said 7 and 9 is that 9 can square root, right? So maybe as a way of demonstrating what's happening, you still have to square root the 7. You can't square root the 7, so it's going to be stuck. But you're then going to try to square root the 9. 9 can actually square root to a 3. All right, now for the letters. You have 5 x's. If you need to, feel free to write them up. There are 1, 2, 3, 4, 5 of them. This time, though, we need them in groups of 2, right? So this is a group of 2. This is a group of 2. And then there's 1 left over. Once you get the hang of it, you don't need to write it out like I am this time here. But really, this is an x squared, which you're going to square root to give you an x on the outside. This is also an x squared, which you'll square root to give you another x on the outside, which we'll just call x squared. That was kind of messy, but that's 3x squared. Give me a funny look. Did I lose you there? Okay. But this x right here, I can't square root it because there's not 2 of them, right? So it has to remain under the square root sign with the 7. So our final answer is there's a 3 that popped out. Each of these came outside as well. And the 7 and the x remained.
How about the one?
So there you go. Oh, thank you, the y's. Okay. Good catch. There are 2 y's. They both come out then. So you go y right there. Is that why you were giving me a funny look?
Nice.
Okay. Does that make sense? Good catch. You guys are paying attention. Okay, another possibility is going backwards. What if I give you a radical that's in a mixed form, and I want you to go backwards and put it into an entire form? That's also a skill I need you to work on. Again, regardless of -1 or -2. So, honestly, I think this one's actually easier. Because all you do then is you say, well, this 7 right here, it must have been under the square root sign twice. Because really, the square rooting of it is what brought it outside. So I have to put 2 7s inside. Or another way of looking at it is it's 2 times a couple of 7s. Well, I just grab my calculator and just say, well, what's 7 times 7? Times 2. That's it. We're just going backwards. It's okay. Okay. Did that one make sense? Okay, let's do the same thing with the variables. All it means then is that you still have the 2x inside. This x is a 3. You have to put it inside the square root sign twice. So maybe I'll write it like this. I'll put it inside once, and I'll put it inside again. How many x's are under the square root sign now? 7. Yeah, exponent rules are there's 1 here, 2, 3, 4, 5, 6, 7. You add them up. So your final answer would be 2x to the 7. Okay, the last one's the one that's going to intimidate you at first. It's probably the one that's the most new, because everything else is probably just a slight tweak on last year.
Yeah.
But this next one here, I don't know how far Quan kind of went with you guys. So, okay. So what I need you guys to get familiar with is if you ever see an exponent that's a fraction, it's the same notation as a square root. So really, this is a fancy way of saying 2k squared, and then under a square root sign is a 3k. Because the bottom of an exponent tells you what type of root there is, and you just need to have it once. So you need both of the 3 and the k under a square root sign. You could put a 1 there, but that's kind of why? Right? That's not helpful. Usually you have to put some. If there was no bracket, it would imply that only the k was square rooted. So what you'd have is you'd have 3k squared 3, and then you'd square root just the k. But because of the bracket, both the 3 and the k go inside it. Alright, so last step then. It's a square root. So, I mean, the 3k is still there. You need to put a 2k squared and another 2k squared underneath. One thing I haven't mentioned though is what operation needs to go in between these. We're always multiplying, by the way. You can pick up on that. Last step, put stuff together. 3 times 2 is 6 times 2, 12. And there's 5k's. Ta-da! That makes sense. Cool. Okay. We're getting close to the end here. I need to show because of the way that I've tried to make this course work with trying to teach Dash 1 and Dash 2, I really had to be very clever about which order I teach things in. Some of you guys in physics have already noticed that it would be nice if I could do things in different order, but my hands are a little bit tied. Ideally, I would have liked to have shown you guys this before we did the quadratic formula, because you know how the quadratic formula has a square root sign in it? The principles I've just shown you apply whenever we do the quadratic formula. And so this is kind of backwards. It would have been nice to have done this in the last unit, but based on the order of how I had to teach things in, what ended up happening was whenever you guys had a quadratic that looked like this, 3 plus or minus root 178 over 6, I told you to stop. But we're actually not going to stop anymore. So whenever quadratics comes back up again, this really applies mostly to Dash 1 students because we're going to use them a lot. This root 178 right here, we need to simplify it. And previously I just kind of let you just stop with it. So, does that kind of make sense what I'm saying? So for kids who are going to do Dash 2, this will matter next year in 30-2. But for right now, not that I'm saying you don't have to pay attention, but it seems less likely you'll have to do this. Because I need to talk about how to simplify things. If there is ever a radicand that has factors in it, we need to simplify it. This second thing, by the way, we'll get to it later. So this second radical not part of a denominator, we'll get to that. So I want to talk to you a bit about quadratics then again. So loop back to the last unit. So if you guys remember how we did quadratic formula, right? This is a very possible answer where you get a number under a square root sign. If the number under the square root sign was a square rootable number, my expectation of you was, well, square root that number to keep going, right? And so like the 25, you can turn into a 5. But what I need now to loop back to is, from now on, whenever you redo quadratics, let's say the number under the square root sign was 720. This is where I used to tell you to stop. I used to say, stop here. But just based on the order in which I taught things, I actually need to tell you that's not true. The whole time we should have actually been keeping going.
Can you please come to the office? Well, Greer, please come to the office.
So you can follow this. 720, a large number. It can get broken down into pieces. One of the pieces is 1, 44, and 5. Why did I choose that? For the 144, right? Because the 144 turned into a 12. Now watch this. This next step loses kids sometimes. Just on the top of the fraction, you see how there's a 24 and a 12? We're going to factor that. We're going to factor out a 12. So if you factor out a 12 out of 24, that's where the 2 came from. And if you factor the 12 off of the root 5, that's why there's still a root 5 here. It's kind of confusing because of the plus minus bit, but just ignore the fact that it's plus minus. Pull a 12 out of 24, leave you with 2. Pull a 12 out of 12, root 5, and you just have a root 5. Now do you see how there's a 12 and an 8 right here? 12 and 8, we can do some canceling. You can divide this by 4 to get 3, divide this by 4 to get 2. Unfortunately, that's as good as it gets, though. Then we re-times the 3 by the 2 and the 3 by the root 5. And this is now the new final answer that I'm going to expect. Okay, so good news, bad news scenario here. Good news if you're in Dash 2. Honestly, this really isn't going to apply anymore because I told you we're done with the quadratic stuff. So, that being said, it will come up again next year. But we'll let future Bauka worry about that. Okay, for you guys that are in my Dash 1 class though, we're still going to be using the quadratic formula, again on a fairly regular basis. I'm sorry, just it never goes away. If you're in my physics class, you're probably sick of it by now. You sick of it by now? No, you're like, this sucks. But it's the only method, it's not the only method, it's the best method we have to deal with things that are squared. And we're going to have things that are squared pretty consistently. So, anyways, does that make sense? From now on, I'm going to need you guys to do some simplifying. So, I just have, what, one example left? Okay, so last example, then we'll give you some time to work on stuff. We want to put this in simplest form. You guys still with me? I need like 3 minutes. So, normally, in the last unit, we were done right here. But I need you guys to be able to go further in the future. It's the root 160 that really matters. So hopefully you'd agree that 160, you got to find at least some perfect square number that times is to 160. I think 16 and 10 is the best option, right? 16 was purposely chosen because it square roots to 4. So I'm going to rewrite this now as minus 4 plus or minus 4 root 10 over 8. Focus only on the top of the fraction for the next little while here. See how there's a 4 in the first little section here? There's also a 4 sitting out there, and a factor out the 4. In doing so, it'll look like this. 4 bracket. Pull a 4 out of minus 4. You have minus 1. Pull the 4 off of the root 10. If you want to, you could write a 1 there, I guess. Like that. Divided by 8. The reason why that's useful, though, is that 4 and 8 as monomials can reduce. 4 and 8 can cancel to a 1 and a 2. So the final answer from now on that I'm going to expect will be minus 1 plus or minus, I'll just say root 10 over 2. On the diploma exam in grade 12, you know the question that I've been asking you that looks like this, negative a plus or minus root b over c? That's been on both of the last 2 diplomas. So I want to make sure you guys are able to handle that, which is why it's been on your test recently. The way you would then answer it is it's 1, 1, 0, 2. Not 4, 1, 6, 0, 8. You see how this top one up here, you wouldn't even be able to do it on a numeric response because there's actually 5 digits. I need you to be able to break it down so there's only 4 digits left. And that has been on, it actually frustrated me a lot as a teacher. The outcome that we actually had to work with was grade 12 stuff. But the way they were testing kids on the diploma, they had to know how to still do this, which is a grade 11 skill. So I found that super frustrating because I felt like I prepared my grade 12 students really well for grade 12 stuff, but they'd forgotten how to do some stuff back in grade 11. So now I'm being really targeted. I'm showing it you now in advance. Okay, quick review then. what I need for you guys to be able to do is basically break down square rooted numbers. But not just numbers, you also have to be able to handle if there's some letters involved, and the transition between like a square root and a fractional exponent. So if it's the power of 1/2, it's a square root. Power of 1/3, it's a cube root. That's all. And then last thing, you need to be able to use that and go back to the quadratic formula. Okay. Tomorrow, or actually not tomorrow, but Tuesday, I made a video which then talks about how to combine these radicals, which basically says that if you have 1√5 and 4√5s, you have 5√5s. If you're kind of to that point and you want to move ahead, I can work with you on that. Okay, last thought, and you guys can take a break. Don't leave early. A lot of you guys did that yesterday. If you're struggling and you're not doing well in class, and you're leaving early, those two things don't jive. There's a time and place for taking off before the bell, but I would say if you're struggling and you're not doing well, it's not going to look good to talk to your parents and be like, you're failing. And then they ask me, and I say, well, what could he do? Well, he could stay in class more often. That's not going to go over well. You know what I'm saying here? So today, although I know it's right before the long weekend, the advice I'd give you, stick around, get some stuff done while I'm here. I mean, I'm still going to let you have the option, but don't ditch out early if you got stuff to do. That's a poor choice. And for sure, you got to sign the board, okay? If you are going to leave, let me know and sign the board. So, anyways, it's 45 minutes before your long weekend. Take a break, but come back and do something. Don't ditch out.